Welcome to This Explainer. Today, we're going to rescue your standard ordinary least squares models from breaking down when your variables start moving in lockstep. Seriously, if you've ever been totally frustrated by models that just swing wildly every time you resample your data, you are absolutely in the right place. We're tackling multicollinearity head-on by mastering ridge regression in R.
But hey, before we dive headfirst into the complex code, we need to challenge our assumptions and prove that a problem actually exists in our data. You see, ridge regression solves one very specific problem: predictors that are highly correlated with each other. If your predictors aren't collinear, reaching for advanced tools like ridge regression actually buys you very little. And honestly, a standard multiple linear regression model is going to be far simpler to interpret. We've got to diagnose the illness before we prescribe the cure.
So here is our roadmap for today. We'll start with the hidden enemy, figure out what ridge regression actually is, go through fitting it in R, compare ridge versus lasso, and finally, cover how to report your results. Let's get right into it.
Section 1, Multicollinearity, the hidden enemy. We're going to use the classic MT-cars dataset as our battleground today. Think about trying to predict miles per gallon using 4 different predictors: engine displacement, horsepower, weight, and quarter-mile time. Now, there's a massive red flag we need to talk about: 0.888. If you run a correlation matrix on those predictors, you'll immediately see that engine displacement and car weight correlate at an enormous 0.888. This means they're moving together almost perfectly in lockstep. They're effectively fighting for the exact same predictive space in your model, and that completely throws off standard regression calculations. That right there is your blaring multicollinearity signal.
But we don't just want to stop at a simple correlation matrix. We want to confirm this issue using the variance inflation factor, or VIF. The absolutely crucial thing to remember is that any VIF over 5 is a problem, and anything over 10 is severe. In this dataset, 3 of our 4 predictors, displacement, weight, and horsepower, are clocking in with a VIF above 5. So this proves beyond a shadow of a doubt that we have a severe multicollinearity issue that standard models simply can't handle. This isn't just a convenient teaching example. It's a legitimate real-world scenario where we absolutely need a different approach.
All right, Section 2, what is ridge regression? Now that we've found the sickness, let's explore exactly how the cure works. Simply put, ridge regression is a regularized version of linear regression. While ordinary least squares just tries to blindly find coefficients that minimize the residual sum of squares, ridge regression stabilizes our model by adding an extra penalty term to that equation. This is known as the L2 penalty, which is basically the sum of the squared coefficients scaled by a parameter called lambda. Think of this lambda parameter like a dial on an amplifier. As you turn it up, the penalty for having volatile coefficients gets heavier and heavier. I love this concept because ridge regression is a variable tamer. It's not a variable killer. As that lambda penalty increases, the coefficients shrink toward 0. But here's the kicker: they never reach exactly 0. Every single predictor stays in the model just with a shrinking, stabilized influence. If you're looking for a model that drops irrelevant predictors completely, ridge isn't your tool. Ridge is all about keeping everything but controlling the chaos. Moving on to Section 3, fitting ridge in R. It's time to take this from theory to execution using the incredibly popular glnet package. Here's the essential 4-step workflow you're going to use. Build your matrix, fit the path, select your optimal lambda, and then refit. The biggest thing to remember here is that glmnet doesn't use that standard formula syntax you're probably used to with a basic LM function. Nope, it explicitly requires you to set up a predictor matrix, which we'll call X, and a response vector, which we'll call Y. Now pay super close attention to this part. When you actually call the glnet function, the absolute most common, completely run-ruining copy-paste error out there is setting the alpha parameter to 1. Setting alpha to 1 fits lasso regression, not ridge. So always double-check that your alpha is set to exactly 0 for ridge regression before you go reporting any results.
Okay, on to step 3, where we figure out how this actually builds our final model. glmnet fits an entire path of 100 lambda values by default, and it's up to you to pick the best one. To do this, we use the cv.glmnet function. This automatically runs 10-fold cross-validation behind the scenes. It basically chops your data into 10 pieces, tests the model repeatedly, and pinpoints the exact penalty amount, that magic lambda, that minimizes your mean cross-validated prediction error. For our specific MT-cars dataset, the cross-validation tells us the absolute best-performing lambda is roughly 5.3. When we take that 5.3 and plug it back into our final model, we get a beautifully stabilized fit that explains about 82% of the variance in miles per gallon. Now, you might be thinking, hey, an unregularized OLS model might give me 84%, so why bother with Ridge? Well, that tiny gap is simply the cost of stability. Ridge trades a microscopic amount of training fit to give you coefficients that won't swing wildly the second you apply them to brand new data. Section 4. Ridge, lasso, or elastic net. Before you finalize your entire model, you've got to be absolutely sure you picked the right regularization tool, especially since all three of these run through the exact same glmnet function just by tweaking that alpha parameter. Here is the crucial breakdown. If you are confident all your predictors are theoretically relevant and you just need to manage their collinearity, you go with Ridge, setting alpha to 0. It uses that L2 penalty we talked about, keeps everything, and just shrinks the coefficients. But if you suspect several predictors in your dataset are totally irrelevant and are just adding noise, Lasso, with an alpha of 1, uses an L1 penalty. It's going to automatically perform variable selection for you by dropping those noisy variables entirely to exact 0. And hey, what if your dataset is just a total mess? Like it has both severe collinearity among some variables and a bunch of completely irrelevant predictors. That's where Elastic Net steps in as the ultimate hybrid compromise. By setting your alpha somewhere between 0 and 1, you essentially get a mix of both the L1 and L2 penalties working together. What's really fascinating here is that on our MT-CARS example, all three of these methods return incredibly similar predictive performance, hovering right around 82 or 83% of variance explained. When performance is literally that close, your choice shouldn't just be about chasing a tiny fraction of an R-squared point. Your choice needs to be driven by the narrative your research actually demands. Are you trying to tell a story where you aggressively selected the most important variables, or are you telling a story where you kept everything theoretically important and just stabilized the math? You've got to choose the method that fits your narrative. Finally, Section 5. Reporting your results. Because let's face it, doing the math is only half the battle. Successfully defending it to a thesis committee or a journal editor is the other half. If you're putting together a professional academic write-up, say in APA style, transparency is everything. Your checklist has to explicitly state your justification for using regularization in the first place. This is exactly where you bring up those high VIF values. You also need to spell out the method you used to pick lambda, like tenfold cross-validation. State the final optimal lambda value, and of course, wrap it up with your final model's performance metrics, like the R-squared and root mean square error. You might actually want to pause and jot down this exact wording. This is an airtight template you can easily adapt for your own dissertation or research paper. Just notice how it hits every single point on our checklist super smoothly in just one paragraph. Given evidence of multicollinearity with a VIF range of 3.13 to 7.99, ridge regression was applied. The optimal shrinkage parameter of 5.34 was selected via tenfold cross-validation, and the final model yielded an R-squared of 0.82. It's incredibly clear, concise, and just super professional. So to wrap things up today, I really want to leave you with this final thought. Look back at your own datasets and ask yourself honestly, have you been letting highly correlated variables wreck your baseline stability just for the illusion of a slightly better fit on your training data? Sometimes letting go of a tiny bit of training accuracy by applying a ridge penalty is exactly what you need to build a robust model that actually survives out in the real world. Go check your VIFs, try out glmnet, and start taming your data today. Thanks so much for